Hello students, this is lesson 4.1, linear momentum. This is quite a challenging topic because the equations we're using require a lot of creative use. The equations themselves are quite easy, but there are many ways to write them. As we go through chapter 4, we'll reach a concept called conservation of momentum, which is profound in physics. It is a concept that's relevant at every scale. Conservation of momentum is relevant for electrons, in which it's very complicated. It's relevant for car safety in collisions, which it's a little easier. And there's the very large. Conservation of momentum is relevant in terms of the Big Bang and other concepts in galaxies and stars. I'm going to start with this lesson by just dropping down the definition of what linear momentum is. I think something to note about this is sometimes we just call it regular momentum. There's linear momentum and there's angular momentum. If I just say momentum, I'm talking about linear. Here's the definition of linear momentum. Linear momentum is the product of an object's mass and velocity. Linear momentum is the product of an object's mass and velocity. That is literally the definition of momentum. You'll notice that it's just an equation. So in my opinion, that's not a good enough explanation. I like to have some qualitative understanding of what it means. So I'm also going to add a second definition for you to write down. It is the ability of an object to continue moving. It is the ability of an object to continue moving. So those two values, mass and velocity, both contribute to an object's ability to keep going. If you have something very heavy, like a freight train, something very high mass like a freight train, it's hard to stop that freight train from moving even if it's going very slow. On the contrary, if you have something very light, something very low mass like a bullet, it's still challenging to stop that object because of its high velocity. So a bullet has low mass and high velocity. A freight train has high mass, low velocity. So with a high mass or a high velocity, it's hard to stop that object. This might be reminiscent of inertia. Pretty much the same concept, except momentum is moving. It has a velocity. Here's the equation for it. P equals m times v. Like I said, the product of m and v. So P stands for momentum. If you consider the units of each of these, you'll find out that the unit of momentum is kilogram meters per second. Why? Well, this is kilograms, this is meters per second. Kilograms times meters per second is kilograms meters per second. And this equation can be used in many ways. I'll give two iterations of it right here that we'll use quite a bit. So this is how you calculate the momentum of one object at a specific instant in time, but I can also add many momentums together in a way that is useful, as we'll see later on. But for now, we just have to know how to do it. By adding the momentum of 1, 2, 3, or 4 or 5 objects together, I get something called total momentum or momentum of the system. So remember, sigma means the sum of. The sum of momentums is, well, the sum of these momentums. You add them together. So 1 represents object 1, 2 represents object 2, 3 represents object 3, and so on and so forth. This could be any number of things. 1,000,000 atoms, 2 planets, 4 cars, whatever. Any number of things. So this is total momentum, aka momentum of the system. So if we're looking at 2 planets, for example, that is a 2-planet system. And the second iteration of this original momentum equation is the change in momentum. If I take mass times a final velocity, I get final momentum. If I take mass times initial velocity, I get initial momentum. By subtracting those two things, I can get a change in momentum. So delta P equals PF minus PO. That's our other starting point. Like I said, there are going to be many ways to write each of these equations, but these two are great starting points in almost any word problem. I'll label that again, change in momentum. So yeah, just try to remember that triangle means change in. So triangle P means change in momentum. Let's see an example of this. And in the example, I want you to see, to figure out which of these are we going to use. The sum of the momentums, the total momentum of the system, or change of momentum. So think about that as we're going through it. So here's our first example. Starting from rest, the engine of a 1,400 kilogram car causes its momentum to increase by 28,000 kilogram meters per second, period. Calculate the final velocity of the car. Starting from rest, the engine of a 1,400 kilogram car causes its momentum to increase by 28,000 kilogram meters per second. Calculate the final velocity of the car. So right away, you should notice that this has final in it. We're being asked to calculate final velocity, which is VF, and although none of these equations have VF in them, this one sticks out among the two because of the final. Also, we're looking at one car, so this total equation doesn't make sense. This equation is useful when you have more than one object, but here we have the car and the engine are moving as one, so this is the more relevant equation. So let's write that down, and we'll have to manipulate the equation so that it's useful mathematically. Delta P equals PF minus PO. The issue with this equation, like I said, is there's no VF in it, but this sticks out to us. Remember, any momentum is mass times velocity, so I'll rewrite it. Delta P equals the mass of the car times the final velocity of the car minus the mass of the car times the initial velocity of the car. So the car is changing speed, therefore its momentum is changing, and it goes from this initial momentum to this final momentum. So we take the starting speed times mass to get initial momentum. We take the final speed times mass to get the final momentum. And from here, you can plug in the numbers, or you can solve symbolically. I like to solve symbolically, so I'm going to do that here. We have all the numbers we need, though. V initial is 0 because it starts from rest. This is m because it's in kilograms. And this right here, I should say, this is the increase in our momentum. So that's delta P. You know what? I'm just going to, I'll solve symbolically, like I said. So I'm going to add MVO, add MVO. So delta P plus MVO equals MVF. And then I'm going to divide both sides by M. I'm not going to show that part. Here's what I get. VF equals delta P plus MVO over M. And so I have a beautiful equation in which I can substitute some values. So the final velocity of this car is 28,000 plus 1,400 times 0. Well, I guess I could have cut that out back here because V initial is 0. That's okay. And divide it by 1,400. In your calculator, you do 28,000 divided by 1,400, or just realize that it's like 280 divided by 14. I don't know if that helps you. So the final velocity of this car is 20.0 meters per second. So notice the equation that we actually use is right here, and it was not really given in the beginning of the notes. It is a rehash of this equation here. And like I said, that's the challenging thing with momentum, is that these equations take many different forms. I'll show you a few right now. So this one, we kind of invented that equation by plugging mv in here. I'm going to rewrite it. Delta P equals mv final minus mv initial. I'm going to put a rectangle around this. This is not an equation I'll provide for you on tests, but if you take good notes, you can refer back to this later. Another thing I can do is take a look at these m's. They're the same number, so I can distribute them out or factor them out like this. Delta P equals m v final minus v initial. Delta P equals m, open parentheses, v final minus v initial, close parentheses. What we did there is kind of like in math class if you had, I don't know, xy plus xz. You could factor the x out and you would have x, y plus z. I don't know if that makes it easier or worse, but we always make that symbol, and it goes right here. Anyway, here's another equation that I'm not going to provide for you, but is true. This is the change in momentum for any object that changes velocity. And a third one, remember, delta is a change in. Right here we have a change in velocity, so I can rewrite it like this, even simpler. Delta P equals m. I shouldn't have put that parentheses. Just delta V. Delta P equals m delta V, because if you take the final velocity, this is just the way delta works. Final anything minus initial anything is the change in that thing. Okay, so here's three equations that you might want to hang on to. I won't be providing those. Hopefully you can see the logic with how they're solved. I recommend you start with that first equation, this one, and see if you can write these three on your own, just by looking at this and plugging in MV. Anyway, let's do one more example. With two parts. Okay. Upon hearing an alarm, a 74-kilogram thief runs right with a velocity of 4.5 meters per second and a 60-kilogram thief runs left with a velocity of 3.5 meters per second calculate the momentum of this two-thief system. Upon hearing an alarm, a 74-kilogram thief runs right with a velocity of 4.5 meters per second, and a 60-kilogram thief runs left with a velocity of 3.5 meters per second. Calculate the momentum of this two-thief system. So if you look back at the new equations, one of them is more obviously useful here. I should focus here. Hold up. What are we doing? We're calculating momentum of this system right there. The system of thieves. There's two thieves, so that means that I'm looking at a system. The total momentum of these thieves is going to be the momentum of the first thief plus the momentum of the second thief. If there were a third person there, I would have to add their momentum as well, but there's only two people, so we just look at those two. We ignore the rest of it. So here's how I would write that. Sigma P equals P1 plus P2. And that's what we're trying to calculate, the total momentum. I don't have a momentum for the first thief, so I'm going to have to plug in MV there. I don't have a momentum for the second thief, so I'll have to plug in MV there. Let's do that now. Delta P equals M1 V1 plus M2 V2. So what's with the numbers? Well, we need to differentiate between the thieves. They each have their own mass, so that's the mass of the first guy, that's the mass of the second guy. They each have their own velocity, so there's their respective velocities. And that's about it. I think that's pretty clear. Let's plug the numbers and get them. Delta P equals 74 times 4.5 plus 60 times 3.5. That's not quite it. Take a look closely. The 60-kilogram thief runs left. So usually when I give you a problem, I'll do my best to draw in the negative. I left that out on purpose just to show you that it's It's kind of important. Got to make sure you have that in there. So what's going to happen here is this guy has a positive momentum. This guy has a negative momentum. So their momentums will cancel part of one another out. They won't cancel fully unless they're equal, which they're not. So I could type that in my calculator all at once. First time around, the answer I got was positive 123 kilogram meter per second. Technically, you need to have the plus sign in there. When you do this on a computer quiz, go ahead and leave the plus sign out. Another thing to note here is our momentum, like our unit for momentum, it doesn't matter that this is a total. It's still kilogram meters per second. Like delta P, sigma P, regular P, they have a unit of kilogram meters per second. So that's the total momentum of the system, the thieves. Pretty easy in my opinion. Just be careful that you have that negative there. Anybody that's moving left has a negative velocity. Anyone moving down has a negative velocity. And then up and right are positives. We're going to do a part B here. Maybe you want to throw an A in here. There's A. So part B will be calculate the change in momentum of thief 2 assuming he starts from rest. Calculate the change in momentum of thief 2 assuming he starts from rest. So if we look at our original equations back here, this is the only one that involves change. And I'm ignoring those 3 that we wrote down later on. Maybe you can pick one out of there. I don't have the final momentum of the first, I don't have the final momentum of this thief. I don't have the initial momentum of him. So I'm going to plug in MV here and MV there. And we'll find something a little challenging. It's hard to name these. Which M is this? Well, of course it's M2, because it's the momentum of the mass of the second thief. Same applies for that mass. What about this velocity? It's not just V final, because we have 2 V finals. We have, one has a velocity of 4.5, one has a velocity of 3.5, and those are both finals. So really, I should say V2 final and V2 initial. So in this chapter, this is going to happen a lot. We're going to have a lot of very descriptive subscripts. V2 final means final velocity of object number 2. V2 initial means initial velocity of object number 2. So it gets pretty complicated. Slow down when you're naming the variables, especially later on when we're looking at many objects at once. So take your time naming these. When you see something crazy like V2O, make sure you know what it means. It's the initial velocity of object number 2. The numbers tell us which object, and the O and the F tell us when. Initial is beginning, final is end. Anyway, we'll plug it in from here. Delta P equals 60 times negative 3.5 minus 60 times 0. It says he starts from rest, so that'll be 0. Really, I didn't even need to include that. So that's negative 210 kilograms meters per second. I think that's just about it for this lesson. Yep, that's just about it. If you have questions, let me know. Please submit these notes on Google Classroom. Thank you for watching. I'll see you soon.